All right. Is the screen visible to everyone? All right. Thank you. I think the recording is on. Yes, the recording is on. Fine. All right. Okay. Without any delay, let's start the session now. Okay. So, as always, we start with a quick introduction. So the course name is Analog VLSI Design. It's an NPTEL MOOC course, massive open online course. Fine. The instructor for this course is Dr. Iman Mandal. He is an assistant professor in the Department of Electrical Engineering at IIT Kanpur. I myself hold these tutorial sessions, these discussion sessions. My name is Mayank Anupam, and I'm a PhD student in the Electrical Engineering Department at IIT Kanpur. Fine. So before starting, now today we will be discussing whatever was covered in week 4. All right. So the quick summary of whatever discussion, whatever things were covered in the week 4 is the following. That is basically we learnt about MOSFETs, right? In week 3, by the end of week 3, we learnt about MOSFETs. We learnt about how what are MOSFETs on a very basic level, right? The device, how the device works on a very crude level. After that, we saw from there we came on to this week 4. Here we saw how to use MOSFET, right? How to use MOSFET for power amplification. So first of all, we studied again the same thing, like it's a non-linear device, so we have to develop the incremental model of this non-linear circuit, of this non-linear device. So MOSFET is a non-linear device. So we developed incremental two-port, we did the incremental two-port analysis of this device, right? We developed, we found out what are the various parameters, of the MOSFET, incremental parameters of the MOSFET. All right. After that, we learnt about again the same thing. If we have a non-linear device, then we also need to bias it, right? We need to find the quiescent point where it will start working, where it has to be biased. Okay, I'm sorry, I have to, I'll have to go off for a bit. Please hold on, okay? Yeah, recording is now in progress. Fine. So yeah, as I was saying, we basically need a MOSFET, correct? We need for MOSFET, since MOSFET is a non-linear device, we learned that in any non-linear device we need to have a certain bias point, right? Quiescent point, and around that we operate our device to get power amplification or whatever. So that is why we learned about how to bias a MOSFET. After that, we went again ahead of that, and we learned how to then, once we are able to bias it, and once we are able to find out what are the small signal parameters, after that we learned how to amplify a signal, right? We gave an incremental small signal, small amplitude signal, and then we saw how does it amplify at the output. Then again, after that we learned that since we are always talking small signals, right? So what happens if the signal is not small anymore, right? what happens if the signal is swinging and it is not small anymore? So in that case there will be some effect, right? So sorry, because of if the signal swing is large, right, so there can be some effect on the operating condition. We assume that there is some operating condition, right, some quiescent point around which the device is working. If we are giving applying a small input signal, then our assumption is that the device does not move too much away, does not move a lot, does not move away from the biasing point, right, does not move a lot away from the biasing point. But that assumption is not valid when our signal swing is large. So in that condition, our operating condition, in that case, our operating condition assumptions can break. So that is what we learned in this, right? And we also learned then how what is the maximum signal swing. Okay, so if you assume that there is a small signal, so how small the signal should be, right? Or what is the maximum level, that the maximum level of the signal that you can apply, so that your assumption of small signal is maintained. And so all those things we learned. So before moving ahead with the problems, I want to know whether you have any doubt in this. Does anyone have any doubt in this, whatever was covered? Okay, all right. So if there is no doubt, then fine. I'll just move ahead with the questions now. Okay. Yeah, just recording.
Sorry, my mic was not working.
Yeah, fine.
Uh,
Go ahead.
Good evening.
Good evening. Yes.
So, my understanding of the saturation and linear boundary is just apply the condition VDS is whether greater than equals to VGS
Yes.
minus threshold or not.
Yes. Correct.
Right.
Correct.
So whenever we are checking whether amplifier is in saturation mode at that boundary, we
Huh.
can make that equal sign other than the greater than or, right? It's
Yes.
VDS equals
Yes.
to VGS.
Yes.
But it's all this is my concept. If it is so, then how to attack math basically? It's all about the numerical in the assignment.
Okay. Today I'll be discussing one of them. Okay.
Okay, fine.
Fine. I hope that will clear it out. Any other thing related to the content that was covered? So in all these points, five heads here. In all of them, do you have any doubt? The content that was covered. Do you have any doubt? Okay. So if no, then I'll just proceed with the problems. So the first problem is a simple problem, but I want to solve it anyway. So this is basically a question on biasing the transistors. Okay. So we have this. Huh, we have this transistor here. We have this transistor here. Now this transistor has a this transistor is biased with a bias voltage of VB. Okay, at the gate. So this is gate, this is drain, this is source. Okay, for simplicity we do not show body terminal also. So but there is a body terminal also. Okay, here for simplicity I have not shown body terminal. Fine. So this is the gate. At the gate we have applied a bias voltage VB. All right. It's a DC voltage. Now there is a supply also VDD, and through that supply we have a resistor RL that is connected to the drain of this MOSFET. All right. So this is a very basic, simple biasing. Okay. This is the most simplest kind of biasing that you can have in a MOSFET. Hmm? So here the question is like the VDD is equal to 10 volts is given. Okay, and W by L is equal to 40 is also given. RL is equal to 10 kilo ohm is also given. VB is equal to 2 volts. Okay, so tell me so now tell me what is the operating region of M1. Using this information, I have the information of W by L of this M1. I have the information of every other thing, mu and Cox, VTH, all those things, RL, everything I have. Now from this information I want to know what is the operating region of M1. So how do I attack this question? How do I attack this question?
So you can find the
Hmm.
uh, VDS from the limiting condition with, and assuming that it is in saturation
Yes.
region,
Good. So
and
first thing,
then yeah.
first thing is we have to assume something, right? Because we cannot proceed without that, because the current equations are different for saturation and for triode region, right? Linear region and saturation, the current equations are different. So we will have to first assume something about it. So let's assume that it is in saturation, right? Assume. So solution number one. So first assume that M1 is in saturation. Okay. After that, we know that then in that condition what happens? The current ID that flows here, what is that equation of ID? Half mu n Cox W over L times VGS minus VTH the whole square, right? Because here we have assumed that the MOSFET does not lambda equal to 0, right? We have assumed lambda equal to 0. If lambda had been there, then there would have been a parameter like this, lambda times VDS. Okay, but lambda we have assumed 0, so fine, this is not there. So this is the equation, right? So after this, we know every term in this, right? So half times what is mu and Cox? It's 100 microampere per volt square, so that is 0.1 milli into W by L is how much? W by L is 40. What is VGS minus VTH? VB is how much? 2 volts, right? So VGS is 2 volts. 2 minus VTH is 1. So 2 minus 1 is 1. 1 square. So how much will this be? 2 milli, right? This is 2 milliamperes, isn't it? Correct? Yes. So it is correct. So it is 2 milliamperes. So ID is equal to 2 milliamperes. So now tell me what will be VDS? How will you find out what is VDS?
Simple VDD minus IRL.
VDD minus I times R, ID times RL. So that is equal to how much? VDD is given as 10 volts minus ID is 2 milliamps into RL is 10 kilo ohms. 10 to power 3. So how much will this be? This and this cancel each other. 10 minus 20. So what is that? 10 minus 10, right?
Yes.
So this clearly is what? Clearly this is
Assumption is incorrect.
correct. Assumption is very incorrect. Extremely incorrect. So this is a negative minus 10 volts. So which means that VDS is negative. Which implies what? Assumption is incorrect. Okay. So now, which means what? Hence, the hence M1 should be in linear region, isn't it? So tell me now again, what is the equation of linear region current? What is it?
Yeah, half
Is
mu
it
n cos
is it half?
cos. Yeah. Yes. No, no, not half. It's mu n cos x w by L.
It is not cos x, it is c ox.
P ox, sorry.
Yeah. So this is the equation, right? Correct equation, isn't it? Am I right? This is the correct equation. So now tell me what is the current from here. Mu n c ox is how much? 0.1 milliampere into W by L is 40. VGS minus VTH we know. How much is that? VGS minus VTH is how much? It is 1 volt, correct? So 1 times VTS minus VDS square by 2. So this is equal to, so ID equals how much? 0.1 into 10 to the power minus 3 into 40. So just ignore this. So 4 into 10 to the power minus 3 into VDS minus VDS square by 2. So how much will this be? Now tell me. I do not know ID. I also don't know VDS. So how do I find it out? How do I solve it? Now, am I stuck, or do I have another information also? You understand? In this equation, I do not know ID. I also don't know VDS. So how do I find both of these? So I need another equation also. Something which relates ID and VDS. How do I know that? What is that another equation?
If we know GM, we can.
Yes, we know GM. No, 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 no. We know that ID is equal to what? VDD minus VD upon RL, right? So in this case, ID, this current ID is equal to what? VDD minus VDS divided by RL, right? Isn't it? The current that is flowing here is VDD minus VDS upon RL. So that information we have. So using that information, we just put it here, that information, that ID is equal to VDD minus VDS upon RL. Correct? So let's put this guy here. Okay, what will we get? So we'll get VDD by RL minus VDS upon RL is equal to 4 into 10 to the power minus 3 VDS minus VDS square by 2, right? Now it's a quadratic equation in VDS, isn't it? So yeah, solving this would be a 4 in RL is what? 4 into 10 to the power minus 3. I'm just taking this RL in the opposite side, in the RHS. So 4 into 10 to the power minus 3 into RL is how much? 10 kilo ohms, right? So 10 into 10 to the power 10 to the power 3. So this is equal to VDS minus VDS square upon 2. Now it is VDD minus VDS is equal to, so this and this cancel each other, 40 times VDS minus 20 times VDS square, correct? Putting everything in the right side only, in the LHS only, we have 20 times VDS square minus 40 times VDS minus VDS plus VDD equals 0, right? And what is VDD? How much is VDD? VDD was equal to 10 volts. So 20 VDS square minus 41 VDS minus plus 10 is equal to 0. So how much will this be? What is value of VDS? Tell me what is value of VDS. What are the roots of this equation, quadratic equation? It will be plus 41, right? Plus minus under root 41 square minus
4AB.
20 into 10 into 4, right? Divided by 2 into 20. So it should be 40, correct? VDS will be 41 upon 40 plus minus under root 41 square minus 200 800. Correct?
800.
By 40.
What?
Okay, so 41 square minus 800. So what do you think? What should be the, I mean, let's not do this. So out of these two, 41 and this guy, which one do you think is going to be larger? So let's quickly calculate now. 41 square minus 800. So it's 881. Okay, this guy is 881. 41 plus minus under root 881 divided by 40. And what is the square root of 881?
29.68.
Yes, 29.61, right? 168. 0.68. So it's 41 plus minus. I have not made any mistake somewhere, right? Because it feels like I have done a mistake somewhere. So VD by RL, this is correct. VDS minus VDS square by 2 is also fine. Okay, fine. So what is VDS? VDS is 41 plus minus 29.68 divided by 40, correct? Alright. Okay. So tell me what will be the values, two values. Let's do this calculation. So one will be 41 plus 29 is how much? It's almost 70, right? 70.68 divided by 40, and other will be 41 minus 29.68, right? This is 11.3832 divided by 40. These are our two voltages. Out of these two, what do you think? Which one do you think is the correct one? Which one do you think is the correct VDS? We have two different values, right, of VDS. Which one do you think is the correct value? So how much will these be? These two be 11.32 by 40. How much is that? It's 0.28 volts, right? And how much is this? This guy, 70.6 divided by 40. 1.767, correct?
Yes.
So out of these two, which one do you think is the correct VDS? Clearly both of these two cannot be true, right?
0.28.
Why is that?
Because
Oh, sorry. Please go ahead.
No, you say now, you were saying something, probably you are correct, tell me.
That is basically VDS should be less than VGS minus.
Yes, exactly, that is why, correct. So we know that it is clearly in the linear region now, right? Which means that VDS should be less than VGS minus VTH. And what is our VGS? 1. VGS minus VTH is 1, right? So VDS has to be less than VGS minus VTH, correct? Since VDS is less than VGS minus VTH, right? So on what is the value of VGS minus VTH? This guy is equal to how much? 1 volt, right? Hence VDS should be equal to 0.28, because 1.767 volts is definitely greater than 1 volt, right? Out of these two, only 0.28, only this guy is less than, right? Less than 1 volt. So the correct answer would be 0.28 volts. So is this clear? Is this clear now?
Yes, yes.
Good. So that concludes the first question. This is clear. Fine. Now tell me, uh, I saw that the transistor is in linear region, but I do not want the transistor to be in linear region, isn't it? I want it to be operating in the saturation region, correct? So, but there is only one handle that I have right now. Let's say I want to put the transistor in saturation region, and but for that I only can change the W by L of the transistor. So tell me, in what direction should I change? Should I increase the W by L to bring it to saturation region, or should I decrease the W by L to push the transistor in the saturation region? What should I do?
Decrease it,
Decrease it. Why do you say that?
because if you decrease it, ID will be less, so RL, the voltage across RL will be less. Then VD will increase, and if VD will increase,
Yes,
then it will
correct.
go beyond.
Exactly. That's the correct line of thinking. See, the thing is that we want to decrease, we want to increase VD, right? We want to increase VD because VD was not sufficient. VDS was not sufficient earlier for it to be in saturation region. So somehow we want to make sure that VD increases. But for VD to increase, there is only one thing that I can do, right? I can only make sure that VD increases when the current, the voltage drop across this resistor RL, the voltage drop across this resistor RL, when it decreases, only then VD will increase. Is that correct? Which means that the current has to reduce. The current has to reduce. That will happen only when we make sure that the W by L of the transistor is reduced, isn't it? Correct? So that is why we have to reduce W by L. So let's go to the second problem now. Solution number 2. So we have to reduce W by L to bring the transistor in saturation region. So now the question will be, the next question is, how low should I how much should I reduce W by L by? That is the question. What is the, I mean, there should be some limit, right? If we cross that, then we will say that the transistor is in saturation region. So what is that limit? After which, when I exceed that limit, the transistor will go into saturation region. What is that limit? How do I find
One
it out?
volt. 1 volt.
Basically,
VDS should be greater than or equal to VGS.
correct. So W by L, decrease W by L so that uh, such that transistor uh, remains at the edge of saturation and linear region.